Euler's method is taking us back to when we worked with differential equations in AB calculus, and this topic used to be part of AB calculus, and they recently switched it to BC only. And it has to do with differential equations. And if you remember, differential equations, they are basically first derivatives. Sometimes they can be second derivatives. I mean, you can look at whichever power you want. But there's some type of function like this that we try to separate the variables with as far as y and x. Now this one in particular, you could just do regular integration with and it wouldn't be a big deal. But there are some where that won't be the case, such as in example 2, right? If you tried to integrate this, you have two types of variables, which is why it's called a differential equation in the form that it's currently written in. And sometimes we can't separate these variables, and so the best we can do is estimate. And this is just a type of estimation approach named after Euler. So it says here, there are times when we need something more than just a general solution. For example, it's sometimes useful to know how a specific solution behaves, including some values that the solution will take. In these cases, we must resort to numerical methods that allow us to approximate these solutions of differential equations. There are many methods we can use. We can use slope fields for these as well. And last year you guys went over something called linearization, also known as tangent line approximations. And that can give us like a decent approximation, but obviously it gets worse the further from that point we get. Today we're going to look at a method devised by Euler in the 18th century that expands upon this idea of a tangent line approximation. So Euler's method involves walking out basically on a tightrope, and basically we are reorienting that tightrope more frequently than simply just saying, okay, at the tangent line, here it is, so the estimate at this point is way off, right? So we can do better than that. And instead use smaller step sizes for approximating that change. So instead of walking along the same line the whole time, which is what we did last year with tangent line approximation or linearization, we will change our tangent lines with each step. And a lot of times they'll tell you how many steps you're going to take, so that usually is given to you in the problem. And then that means we have to do a lot of calculations, unfortunately. And this will produce a more accurate approximation at the end than if we had simply continued on that original tangent. So, it's not hard, it's just a lot of steps, but it's repetitive. And I'm just going to kind of jump in for you rather than just talk about it because we use a table for this. So this is the way we're going to set the table up every time. And for you to get credit on a free response question, you have to have these columns labeled or they will not accept it. And that is an important thing to realize. There is another method using linearization that is way more tedious, and so I don't really go over that. I only do tabular, but yes, you do have to know what each column is labeled because that's a requirement to get credit for it. So basically the first thing we do is we have some sort of starting point, and then they tell us some sort of step amount they want us to take, and we figure out what that change in x will have to be so that we take like 4 steps between 0 and 2 or what have you. And then we just go through the line. They have to give you some sort of equation for your slope and some sort of start value so that you know how to start your first tightrope section, so to speak. So you get your starting point, you plug in your x and y into the slope equation, and then you find the change in y by multiplying that rate of change times the step length. And then when you get that change in y, you add it to your original y to get your new y. So blah, 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 all this isn't going to really make sense until we just do a problem. So let's jump into example 1. It says, given the differential equation here, x minus 2, and the initial position y of 0 equals 5, find a position for y of 0.8 by using Euler's method with 2 equal steps. So first let's calculate our step length, so to speak, from 0 to 0.8 if we're taking 2 equal steps. So typically I just do the change in x divided by how many steps they want us to take. And so in this case we're going to be going by steps that are equal to 0.4. So let's label our columns. Okay, so we start at an x position of 0. I like to go ahead and label all the x values I'm going to be looking at. And then I can go ahead and substitute in the y value I was given to start with, which was 5. So at 0, we're at 5. So now I'm going to use my slope equation here to find what the slope at 0, 5 is. So that's just going to be 0 minus 2, which is negative 2. Then if I am doing that rate of change for a distance or a change in x of 0.4, I'm going to have negative 2 times 0.4, which equals negative 0.8. And then that's the amount I add from my original y to get my new y. So my original y was 5, and now I'm going to add that change in y we've calculated, which means that my new y is at 4.2. Okay, and when I get 4.2, that comes all the way over here in my table for me to start the next row with. So it's a recursive pattern. You're taking your previous step and working from there. So same process. So now my slope, again, this particular slope is only really relying on your x value. Sometimes they rely on both. So this is going to be 0.4 minus 2, which is negative 1.6. So I'm doing that change for 0.4 of a step, which is going to give me something kind of gross, negative 0.64, I guess. So I take my original y, which was again the previous step, and I add that delta y, and I get my position 3.56, and this is again actually what you were looking for. This is the estimated y value at 0.8. And so when you write your answer to a question like this, it's best to use function notation and to use your estimate symbols so that we understand it truly is an approximation. Okay? All right, and now for part B, they want us to actually solve the differential equation with that initial condition and estimate with that approach instead. So if you remember, when we're working with these differential equations, we separate the variables. So in this case, that would give us dy equals x minus 2 times dx. And then we would want to integrate both sides with respect to the variables. So dy simply becomes y. X becomes 1/2 x squared. 2 becomes 2x. And then we need a plus c. And then we have the initial condition 0, 5. So if we plug that in, and solve for c, right, both of those things are going to go away and just give us this. So we have the equation y equals 1/2 x squared minus 2x plus 5. And then they want us to actually estimate what's y of 0.8. And so we can substitute that in. If I can fit that. And whenever we do that, we're going to get 3.72. So this is the exact answer versus the estimated, right? So obviously if we can do this method, we tend to. The reason Euler's method is especially helpful is because sometimes we're given differential equations with which we can't separate the variables and do this approach. So then this is our only option. But as you can see, this is the exact and this is the estimated.